All right, welcome to this explainer. Today we're taking on a topic that, honestly, often makes students and data analysts break into a cold sweat. Yep, we're talking about standard deviation, specifically for continuous series. But hey, don't worry. My goal today is to help you confidently calculate this using 3 distinct methods, and we're going to do it without getting totally overwhelmed by all the math.
Here's our instructional ladder for today. We'll start by decoding the symbols, then look at the direct method, the shortcut method, and step deviation, before finally wrapping up with why dispersion actually matters.
Section 1. Decoding the symbols. Understanding the math.
You know, looking at statistical formulas can sometimes feel a bit like trying to read an alien language. But before we crack that code, we really need to understand what standard deviation is actually measuring in the first place, and that is dispersion. According to our source material, dispersion shows the extent to which various values of the series tend to disperse from each other, or from the average. Basically, it's just a fancy way of measuring exactly how spread out our data points really are.
Okay, let's dive right into this. Think of this as your decoder ring for the formulas we'll be using for continuous series. N stands for the total number of observations. M is the midpoint of a class interval. F represents frequency. A is our assumed mean, and C stands for the class interval. So, lock these in your memory. They are absolutely crucial. They're basically the fundamental building blocks for everything we're about to do.
Section 2. The direct method, our baseline approach.
So, the direct method. It's conceptually pretty straightforward, but I'll be honest, it can get mathematically tedious. Here, standard deviation, which is represented by that Greek letter sigma, is equal to the square root of the sum of f times x squared, all divided by n. Now, it looks remarkably compact right there, but there's actually a very specific sequence of actions hidden inside that little x.
Let's break that formula down into 4 actionable steps for a continuous series. Step 1, you find the midpoint, which we call M, for each of your classes. Step 2, calculate the actual mean of your entire data set. You'll often see this represented as x bar. Step 3, find the deviations. This right here is exactly where that little x comes from in our formula. We take the midpoint, M, and subtract the actual mean, x bar. And finally, step 4, we square those individual deviations and multiply them by their corresponding frequency, f. Sum all of that up, divide by n, take the square root, and boom, you have successfully calculated your standard deviation. Section 3, the shortcut method, simplifying deviations. All right, here's a little secret for you. Mathematicians are efficiently lazy. Whenever the actual mean gives us messy decimals, we use this shortcut method formula. And yeah, I know, it looks twice as long, right? But the actual arithmetic is so much shorter because instead of x, we're working with a brand new variable, d. Step 1 introduces the absolute magic of the assumed mean, which is represented by A. Instead of finding the exact messy actual mean, you just pick a convenient middle value to act as your mean. Easy, right? Step 2, find your new deviations, d, by subtracting this assumed mean, a, from your midpoints, m. Then for steps 3 and 4, you calculate the sum of f times d and the sum of f times d squared. By plugging these sums into the formula we just saw, you get the exact same standard deviation, but you completely bypass the headache of calculating that actual mean. Section 4, step deviation, designed for large data sets. If the shortcut method is a great tool, well, this one is literally the ultimate boss-level shortcut. Now, what's really interesting here is the introduction of 2 new elements, d prime inside the square root and c sitting just outside of it at the very end. These small additions, they are going to make your mathematical life incredibly easy.
Okay, let's walk through the steps to unlock this advanced method. Step 1, just like before, find your deviation d by subtracting the assumed mean a from the midpoint m. But step 2, this is the brilliant part. We find d prime by taking d and dividing it by the class interval c. This dramatically scales down your numbers. I mean, it turns intimidating double or triple digits into simple 1s, 2s, and 3s. Step 3, calculate f times d prime and f times d prime squared. Finally, step 4, after you run those tiny, easy-to-manage numbers through the square root formula, you just multiply the final root by c to scale everything back up. It's an absolutely ingenious way to sidestep heavy arithmetic.
Section 5. Why it matters. Analyzing dispersion.
So we've just gone through a whole lot of mathematical mechanics, but why do we care which method to use? Actually, why do we even care about measuring dispersion at all? Well, this table perfectly summarizes our statistical toolkit.
If you have a small dataset with friendly numbers, the direct method, using the actual mean, works just fine. But if you're dealing with a moderate dataset where the actual mean turns into a messy fraction or decimal, you'll definitely want to shift to the shortcut method and use an assumed mean. And if you're tackling a massive, continuous series with uniform class intervals, that step deviation method, the one that divides by the class interval c, is going to save you a ton of time. Basically, choosing the right tool depends entirely on the complexity of your dataset.
Before we wrap up, I want to leave you with a final thought to ponder. We know standard deviation measures how spread out our data is, right? But because these formulas actually require us to square the deviations, those larger spreads end up carrying much more mathematical weight. So, if every dataset has outliers, does standard deviation reveal the true nature of the series, or does it just amplify the extremes? Understanding the how behind these formulas, whether you're using the direct, shortcut, or step deviation method, doesn't just help you calculate a number, it makes you a much sharper, more critical data analyst. Thanks for joining me on this explainer, and as always, keep questioning the data.